Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Jamil Ishaku Abdurrahman and I'm here to explain about the RLC circuit. So, firstly, RLC circuit is the combination of three elements which are the resistor, inductor L and the capacitor C. The symbol for the resistor is this one, which implies the resistor, while for the inductor is this one, which implies the inductor, and the capacitor, which is this one. So here are the three elements for the RLC circuit. So firstly, we are going to start by defining what is resistor. Resistor opposes the flow of current by dissipating energy as heat or losing energy in the form of heat. Secondly, the inductor opposes the changes in current by storing energy in a magnetic field, and the capacitor opposes the changes in voltage by storing energy in an electric field. These three components, R, L, and C, can be connected in series or parallel based on the arrangement of the circuit. But let me show you an example of series connection for the RLC circuit. Assuming here the resistor, the capacitor, and the inductor all arranged in series. Here is the resistor, here is the capacitor, here is the inductor based on their shape. So, firstly, we are going to explain about the voltage and current relationship for each component of the RLC circuit. So now, starting from the resistor, the voltage resistor. So the voltage across the resistor is proportional to the current flowing through it. We know from the definition that the voltage across the resistor is proportional to the what? To the current that time. The current V equals to IR, okay? Because it lose energy, it makes to lose energy. And we have it through the inductor L. So the voltage across the inductor is proportional to the rate of change of the current, that is proportional to how fast the current is changing over time. We are going to do it like this: voltage across the inductor. So we know that inductor store energy in its magnetic field and opposes the changes in what? In the current. We have the third one, which is the capacitor. So the voltage across the capacitor is related to the amount of charges it stores in the capacitor. Since the current is the rate of change of time, so we are going to have a equation like this one. So the voltage across the capacitor is going to be like this, since we have a relationship which includes which is equals to 1 all over capacitance times current dt. Okay, since capacitor store energy in an electric field and opposite changes in voltage. So now we are moving to the Kirchhoff's law. Kirchhoff's Kirchhoff voltage law. So sorry please for the minimum amount of time we have. I cannot write the full law for the Kirchhoff's law because it's somehow broad, but I'm going to read it out. So the Kirchhoff's voltage law states that the sum of all the voltage drop in a closed loop must equal the applied voltage. That is for the RLC, which means here must be equal to all voltage across the resistor, voltage across the inductor, and voltage across the capacitor. So if we substitute these formulas above into this one, we are going to have it like this. Plus L, that is the inductor across the inductor, times di all over dt, plus 1 all over c times I t dt. So we substitute all these equations above with this one and continue for the continuation for the RLC circuit. We are now going to simplify to the second order of differential equation for the series RLC circuit. We are going to have it like this. The inductor times d square I all over dt square plus r times dit all over dt. This one is the second order for the differential equation of the Kirchhoff's law. So now this is the second order for the differential equation of the Kirchhoff's law. Now we are going to move into the behavior of the RLC circuit. Behavior of the RLC circuit. So now on, the behavior of the RLC circuit depends on the relationship between the resistor, inductor, and capacitor. The system can oscillate, damp, and resonate based on the value of the resistor, inductor, and the capacitor. We have the resonance. We have what we call resonance. First of all, what is resonance? Resonance occurs when the inductive reactance and the capacitive reactance are equal, which means they cancel each other out. This happens, the formula for the resonance frequency equals to 1 all over 2 pi root of LC, which implies that at resonance frequency, the inductive reactance is equal to the capacitive reactance. At resonance, the inductive reactance is equal to the capacitive reactance. So, we are moving to the damping. The presence of resistor introduces damping, which affects how the circuit oscillates. We have three types of damping, which is underdamped, when the circuit oscillates with gradually decreasing amplitude. We have the critically damped, when the circuit returns to equilibrium as quickly as possible without oscillating. And we have the overdamped, which means above damp, when the circuit returns to equilibrium slowly without oscillating. We have what we call impedance in RLC circuit. So the formula for the impedance is Z, which is equals to root of R square plus inductive reactance minus capacitive reactance square. So with this, we came to the end of our video. I think it's going to be very important for us, but let me define what impedance. Impedance of a RLC is the total opposition to the flow of current, which combine the resistance and reactance from the inductor and capacitor. Impedance is frequency dependent, and it is given by this. So this is the formula for impedance, and this is all what I have for the RLC circuit. Thank you for your cooperation and time. Thank you for listening. See you later.